Now so then what we will get the velocity value Vf, that will be Vf into 1 minus exponential minus t by 2. From then if we plot the value with respect to the time, then it will get a constant value at a particular time, saturated value, and the tau value which will be 10 to the power minus 10 seconds range. Okay. So basically then we can write that the number of electron per unit volume is Nf, and the velocity then J will be Nf Vf into E. Okay, then sigma will be Nf E square tau by m. And so these are the basic thing which is related to the electrical conductivity. Now we go to the thermal conductivity. So as I told that temperature heat can transfer in three ways. So first one is conduction, convection and radiation. So what is conduction? So the heat can transfer through the atoms like hot to colder region, that will happen within in a solids. Okay, that is conduction. Convection will be which are happening normally in the liquids and gases. So there what will happen, if you take a water in a flask or something, if you boil it, what will happen, the heat will transfer to the below level and it will go up, and similarly this movement will happen of the atomic movement will happen, then heat will transfer in uniformly everywhere in the volume. Okay, and radiation is nothing but we know that electromagnetic radiation, it's heat from the sun to earth, that same thing. Okay, now conduction with we have concentration is thermal conductivity, which is nothing but the conduction with the electron movement. Okay, so transport of heat per unit volume, we can unit conventional area and per unit temperature gradient, that is thermal conductivity. So what is thermal conductivity? Transport of heat per unit time, unit cross sectional area and unit temperature gradient. So that we can write it as minus 1 by q by t divided by delta t by delta x. So that will be jq divided by dt by dx. So jq, that is nothing but heat flux. Okay, so from the heat flux jq we can write it as minus k dt by dx, and that will be calling as Fourier law of heat condition. Now let us take a sample. One end will be hot, other end is cold. So we are considering this is the x direction, so we are considering a point here x. Okay, now normally the energy function of the here, the heat energy which transfer, that is nothing but the function of temperature. So energy is the function of temperature, and temperature, that is function of x. So we can write it as E of T of x. And now what will happen normally, when hot end, if we any get electron, it's move, there will happen a collision, right? So if a hot end there will see electron, and cold end another electron, it will get a collision, then heat energy will transfer to the cold atom, cold electrons, right? So in the last, we are considering a point that is at x. So the last collision which happened is v2. Then if before x some place, that will be vx minus v2, then we can write the flux that will be nf by 2 v e of t into t of x minus v2. Similarly jq, that nf by 2 v epsilon t into x plus v2 we can write. So net flux will be what, hot to cold and minus cold to hot end. So that will be this is the steps which we have followed in the class. Then we can get the j value, that will be minus k dt by dx. So from there we can write k is equal to 1 by 3 v square tau cv. C nothing but specific heat, and v square is the average velocity. Okay, so this is the one another formula which you have to remember for the thermal conductivity part. Now let us go to the success and limitations of the Drude model. So in Drude model what we have learned, first one is from using Drude model we can get the value of electrical conductivity as well as the thermal conductivity. So that are the two formula. Electrical conductivity will be nf e square tau by m, and the thermal conductivity will be 1 by 3 v square tau cv. Okay. No, so basic idea is that what the electrons are doing both the process. Like for example, idea what we have used is, for example, we have a material that is insulating nature, so then you have an atomic vibration providing the path for the heat conduction, so to speak, so that we know something that we have included in the picture. So that's what accordingly which parameter we have used. Now then Sarah discussed about the engineering cooling systems and where we can use that and all. Now there is another two scientists, Weidman and Franz. They were taken a lot of metallic system and found that the room temperature and or at the same temperature follow the ratio of the thermal conductivity to the electrical conductivity will be constant. So k by sigma t, that will be constant, and it is around 2.4 into 10 to the minus 8. That's what they have found it, and which is like empirical law. So this we are calling as Weidman-Franz law. In Drude model they enable actually to make the come up with the kind of constant for the Weidman-Franz law to see if this Drude model is consistent finding with this law. So for seeing that we have calculated the value using the formula and almost got the value 1.1 into 10 to the minus 8. So it's nearly equal value. So in Drude model can tell about the Weidman-Franz law, and not Drude model is not only predicting the independently the thermal conductivity and independently the electrical conductivity of matter, it also give us the result consistent with the Weidman-Franz law. So that is the one of the advantage for the Drude's model. Okay, and these three things are successful for this model. This model actually does a good job in predicting the experiment data in all of the three this category. One is thermal conductivity, electrical conductivity, as well as Weidman-Franz law. Now something, for example, something if it is belong to gases and pushing it, taking a theory that belong to gases or pushing into something that exists within the solid. So that's what we have done, right? We have started from kinetic theory and we gave some some limit changes and we made a theory for the solids. Okay, there is a reason so there is reason to be cautioned about this, because the number density of particle in 3 or is 3 order of the magnitude is higher in solids. So that given that you need to be cautious, and therefore there is something that we need to be careful about it. So despite of this reason question, we find that the major results actually pretty good. So only one thing is, we compare to gases to solids, the number of atom will be more. So that thing we have to be in mind, because the interaction will be higher in the solids. And there will be couple of errors, which when we use the Doots model, basically in the electrical contribution of the specific heat, that is overestimated. So normally electrical specific heat is overestimated with 100 times more than that the actual value. Similarly, the square velocity, v square value, whatever the formula of thermal conductivity, that is the underestimated by the 100. So by these two factors, when we all are coming as a multiplication, it is coming as a correct answer. Okay, so each separately, if we consider the values like velocity or otherwise specific heat and all, what will happen, it is overestimating or underestimating the exact values. Okay, and this model actually predict the Hall effect also. So what is all of it? For a conducting material, the current is flowing in this direction. So Jx we have written, and if you apply perpendicular direction magnetic field, what will happen? The charge carriers will split into two directions. One is positive and another negative direction. Now the will be a coefficient, Hall coefficient. That is, if it is negative, mean it depends on the voltage sign. Waiting but the Hall coefficient voltage sign, we can understand the what are the charge carriers which is present in the material. Okay, so if it is negative, and if the Hall coefficient is negative, then we can understand it is a negative charge carrier, nothing but electrons. If it is positive, then it will be a positive charge carrier, holes example. Okay, dot model is correctly only when for the negative charge carriers, because mainly for electron, not for the other any charge carriers. So these are the main topic which are discussed in the classes. So you should remember all this topic. Okay, and the formula whatever represented in the class. Now we will go to the few problem sessions. Hope you can see the PPT. First we will go through few problems which we have solved in the last classes, because free electron theory also important for the exam. So we will go through few problems, then we will go to this week's sections. Okay, so hope you can see the screen. First we will go to the problem. Determine the volume occupied by 2.34 grams of carbon dioxide at STP. So here we know that the formula, ideal gas formula, PV is equal to nRC. From there you calculate volume V, that is equal to nRT by P, and substitute the values, you will get the answer, volume in liters. So please do it first, then we will go to the other problem. Let us see the second problem. A sample of argon gas at STP occupies 56.2 liter. Determine the number of moles of argon at the mass of the argon is in the sample. So here what we have to do, we have to rearrange the again ideal gas equation, that N is equal to Pp by RT. Substitute the value, so in 180 m liter, and the other values for the R and temperature, then we will get the value of moles. It will be, that is equal to 2.50 moles. Then multiply that moles with the weight, atomic weight, then you will get the total number of gram which is present in this. Okay. Let's go through this problem, then we will go to the other one. Now we'll go to the third problem. At what temperature will 0.654 moles of neon gas occupy 12.30 liters at 1.95 atmosphere? So here also ideal gas equation we have to use. T is equal to PV by NR. Substitute the values, we will get the temperature. So these problems are very easy, but you have to remember one thing, that units whatever you are using, everything should be proper units, then only you will get the answer correctly. Otherwise you will get the answer digital may be different. Let us see the fourth problem. A 30.6 gram sample of gas occupied 22.414 liter at STP. So what is the molecular weight of the gas? Since one mole of gas occupied this 22.414 liter STP, then molar weight will be 30.6 gram per mole. Now let us see the fifth problem. A 40 gram of gas sample occupied 11.2 liter STP. Find the molecular weight of the gas. So 11.2 STP means half of the molar volume. So it will be 0.5 moles of gas present. Therefore molecular weight will be half of it. Mean double, that will be 80 gram per mole. Okay. You go to the problem, that is here 112 gram of sample of gas occupies 19.2 liter of STP. What is the molecular weight of the gas? So this problem, as well as to judge about chemical, PVC equal to NRT. So PVC equal to NRT, we will get from there substitute the value, then N we will get it. If you know the molecular weight, what will be 12 gram divided by atomic mass, so that number of moles that we will get is 14 grams. So since it is STP, so 19.2 divided by 12 gram, that will be is equal to 22.414 divided by x, then you will get how much gram will be present in that. So it should be now we go to the other one. Problem 7, that is 96 gram of water occupies 48 liter and 700 millimeter mercury and 20 degrees Celsius. What is the molecular weight? So solving that, we have to find the number of moles first, dividing by the weight. Atomic weight means molecular weight, we will get the given weight by the molar mass, mole number of moles, we will get the molar mass. So this is also very easy problem. If you do the ideal gas equation very clearly, then you can easily find the answer for this. Now we go to the other problem. 20.83 gram of gas occupies 4.6167 liter at the 79.97 kilopascal at 30 degrees Celsius. What is the molecular weight? So here we have to solve first, find the number of moles from ideal gas equation. From the we have to divide the number of moles from the given one, then we will get the molecular weight. So same as like earlier problem, we have to just substitute the values of now see this problem. 5.6 gram of solid CO carbon dioxide is put in empty sealed 4.0 liter container at the temperature 300 Kelvin. When all the solids CO2 become gas, what will be the pressure of the container? First, we have to find the moles of carbon dioxide, that given mass by molecular mass, we will get it, and PV is equal to nRC. From there, we have to find the pressure of the carbon dioxide in the gas form. Now we'll go to these problems. It's theory problems. So first question, resistance of a conductor. So the options which is given: decreases with increasing the cross-sectional area, decreases with increasing the length, is a constant independent of length, and increase with increasing temperature. So first we discussed today's class, that is like R is equal to rho into L by A. So definitely what will be the answer will be so here answer will be it is decreases with increasing the cross-sectional area, because area will be in the denominator. And similarly increasing with increasing of the length. So here length is in the numerator, so if the length value increases, then increase with increasing the length. Now see the conductivity of a metallic conductor. What will be the possible answers of this? So conductivity is nothing but 1 by rho. So if you fix a material with a particular volume, so we cannot say that increasing with alloying. Okay. Similarly, increasing the presence of grain boundary, that is also wrong answer, because it will not increase in the presence of the ground boundary. So it will be fixed volume, it will be same. So decreases with presence of porosity, that is correct, and decrease with presence of precipitate. Now let us go to the other problem. When the voltage applied to a conductor is gradually increased. So voltage increased, what will happen? So just we have to think about Ohm's law, V is equal to IR, that we can write, and rho L by E. Okay, so it will be like I 1 by sigma L by E. So what will be the answer for this? So first option, the current gradually increases, that is correct, because it is proportional. So second option, the resistance gradually increases, that is wrong, because resistance is a material property, it will not increase. If it depends on the material, it will be there. Okay. And the power consumption will increase and electric field will be decreased, that is also wrong. The fourth question, in an infinitely long metal wire, if two free electrons are 1 meter apart and the wire is subjected to an electric field epsilon, then both electrons will initially accelerate. If it is possible that electrons can meet, the electrons are behind them with accelerating more slowly. The two electrons will prevent each other from moving. So here electrons moves randomly, right? If electrons move randomly, what will happen? If it is possible that the electron can meet, and both electrons will initially accelerate. And what about the other options? Electrons behind will accelerate more slowly. That is not correct. And the two electrons will prevent each other from the moving. That's also not correct. Okay. Now see this question. In a metallic conductor at room temperature in the presence of an applied field. So what will happen? The average velocity of the electron is 0. That is wrong. So definitely nay. And the instant velocity of electron is 0. The average electron is not 0. That is correct. And the average speed of electron is not correct. So what will be the formula? Vf is equal to E tau by m, and V is equal to root of so heat can transfer in a metal through what? Conduction. Okay. So see the next question. Atomic vibrations are primary mode of heat transfer in all the metal at room temperature. For a metal, atomic vibration is not, what is that for nonce? So in metal, no, atomic vibration is not the primary mode of transfer. It is the free electrons. So the answer is false. So calculate the electrical conductivity of a trivalent metal having atom number 13 in ohm inverse meter inverse. So it's given two hints that trivalent metal and atomic number 13. So atomic number 13 means which element it is? It is aluminium, it's a metal. see here what we have to do is, so first we know that the conductivity value NF is square tau by m. So from here E is constant and time period we already know that in the class it will be 10 to the power minus 14 seconds order, and mass also we know. Now what we have to calculate, first we have to calculate n value. So n value, that from the density by mass we can calculate the volume, and then it will be like 2.7 10 to the power 6 gram per meter square. Then if you multiply that mass 27 into 10 to the power 6, you will get that number of atoms. So that many number of atom will be there, like the 2.7 divided by 27 into 6 into 10 to the power 23, and each atom will give 3 electrons because it is trivalent metal. So then you have to multiply 3, so total number of electrons will be this much. Now this number and all these values constants we have to substitute in the formula, and we will get the conductivity value in order of 10 to the power 7. Now see this question, calculate the mean free time for a positive charge mass 9.1 into 10 to the minus 31 kilogram when placed in extended field of 1 volt per meter. So we know that the formula of velocity, that is E tau by m. From there you find the time period, that is Vf m by E, that is electric field and charge of electron and the velocity and mass. And we know the current density formula, NFEAVF. So substitute those values here and you will get the answer in terms of 10 to the power minus 14 seconds. Let us move to the other problem. A heat exchanger in your laptop is the combination of copper, metal tubes and fans. Because why? The reasons are copper is a good thermal conductor, as well as the copper conduct the heat and the fan blows out into the bring to the cool air. Okay. And see the fifth question. The Weidmann-Franz law is the ratio of electrical and thermal conductivity. So the Roots and Lorentz model is successfully in theoretically predicting this is because too wrong estimated estimating the model compensate of each other, because we know that the value how the Weidmann-Lorentz law is satisfied by the Roots model. We know that Roots model, which is estimating the electrical conductivity value in power terms of 10 to the 100 order. Similarly, underestimating the value of the velocity square. So if you get these two values, then the answer whatever we are getting in Weidmann-Franz law, which is obeying by the Roots model. And this we have already discussed. Now let us go to this few mathematical problems. Consider a metal with a number density of free electron n is equal to 8.5 into 10 to the power 20 square meter cube per meter cube, and the electron charge is equal to 1.6 into 10 to the power minus 19 coulomb, and if the mean free time between collision is tau, that is equal to 2.5 into 10 to the power minus 14 second. Calculate the electrical conductivity of the metal using the Root model. So we know the formula conductivity, that will be n e square tau by m. So m is the mass of electron, that is m 9.1 into 10 to the power minus 31 kilogram is the mass of the electron. Substitute those values here. So we will get 8.5 into 10 to the power 28 meter per meter cube, and 1.6 into 10 to the power minus 19 coulomb square into 2.5 into 10 to the power minus 14 seconds divided by the mass of the electron. Then you will get the conductivity value. Okay, we will go to the next problem. A metal has electrical conductivity 5.8 into 10 to the power second Siemens per meter at the room temperature. Using the Weigman-Franz law, estimate the thermal conductivity of the metal at room temperature. The Lorentz number which L is given. Okay, so we know that the Weigman-Franz law of thermal conductivity K and electrical sigma, it will be K by sigma is equal to LT. From there we have to compute the thermal conductivity. So K is equal to sigma LT. Substitute all the value, you will get the thermal conductivity. Go to the other problem. Using the Drude's model, calculate the mean free path lambda of the electrons in a metal with the following parameter: electron velocity Vf is equal to 1.57 into 10 to the power 6 meter per second, and mean free path mean free time tau is equal to 2 into 10 to the power minus 14 second. Okay, so what is the mean free path lambda will be? Lambda is equal to Vf into time, like nothing but distance, is equal to velocity in time. Same logic. Now let us go to the other problem. In a metal, the mean free time T is inversely proportional to the temperature T. If the electric conductivity of the metal sigma 0 at the time temperature T0, find the electrical conductivity sigma at new temperature T. So we know that tau, which is inversely proportional to temperature, so electrical conductivity sigma at the temperature T can be expressed as sigma is equal to sigma 0 T0 divided by T. Let us go to the other problem. The resistivity rho is of a metal at room temperature is 1.7 × 10 to the power minus 8 ohm meter. Given the number density of the free electron N is equal to 5.9 × 10 to the power 28 per meter cube. Calculate the mean free time tau using Roots model. Electron charge is given, mass of electron also given. So we know that is direct formula rho is equal to me divided by Na square tau. And rearrange for the time, then it will be tau is equal to me by rho n e square. Then substitute the value, you will get the mean free time. Now we will go to other problem. A material has electrical conductivity sigma is equal to 2.1 into 10 to the power 6 Siemens per meter, and thermal conductivity K is equal to 230 Weber per meter, watts per meter Kelvin, and at room temperature. And using the Wehrmann-Franz law, determine the mean free time for the electron. Assume the Lorentz number which is given and the number density also given. So we know that K is equal to sigma LT. From the value, we have to find the value of sigma, the thermal conductivity, and L and T value which is given. We will get the sigma value, that will be 3.1 into 10 to the power 7 Siemens per meter. And then using the Roots formula, what we have to do, tau is equal to sigma me by Ne square. We have to find the value of the mean free time. So we will stop today's section here. So please go through the problem whatever we have discussed in the classroom. Okay, see you next week.